Okay, so we'll head on into this. Just a brief show of hands, if you don't mind. How many people were here for the previous presentation? Okay, probably about a third, a half, something along those lines. Okay. So obviously in this presentation we're going to repeat some of the information to bring everybody up to speed, and then we'll look more at how we start to develop advanced IoT security and solutions. And again, the intent of this presentation is to introduce you to the capabilities. It's not intended to be a complete teardown of a solution. If you have those questions, we're happy to talk about those afterwards, but hopefully there'll be some more information in here for everybody. As before, if you have a question, if it's relevant to the specific point and it's a pretty sharp question, please shout out. Otherwise, I'm sure we'll have time at the end of the session for some more formal Q&A. Okay. So, advanced IoT security. My name again is Hayden Povey. I'm the CEO of a company called Secure Things. We're a security consultancy. We were set up in 2014 to really focus on these rapidly evolving security issues in the IoT space. And we've been working very closely with Renesas around developing some of the capabilities and making the most of the technologies in the new Synergy platform. So we do a bunch of things. Secure Thinking is our consultancy service capability there. And so, you know, why me? Why am I up here? And why do I know about security? Well, previous to setting up the company, I was director of security technology at Arm. And that covered a very wide array of technologies, applications, and partnerships, from technology which went into SIMs, bank cards, other secure elements, tamper-resistant security with Arm's Secure Core, all the way up to Trust Zone, which is technology, security technology in handsets, tablets, servers, and moving into another array of devices. Through this, of course, you know, we were defining what security looked like in the ARM architecture, but also working very closely with OEMs, network operators, and others to understand how they would use security technology, build it out, and all of the different aspects of that, from creation of devices to delivery of complex systems. Prior to that, I was director of embedded processors at ARM. I was the original lead on the Cortex-M3 and all of the Cortex-M processors. So they're all my babies in one way or another. And of course, you know, those have been very successful. And finally, we got Renesas to catch on and move to the Cortex family. But, you know, we got there eventually. So, we're, you know, I'm now out on the outside, or just before that again, prior to ARM, I spent 10 years in the US and Europe working for National Instruments, and again worked with a lot of military, aerospace, automotive customers, so understanding the requirements of real-world systems, deterministic systems, applications where if something goes wrong, things tend to explode or go bang. So a good background on really all things security, capabilities for those, requirement for those as well. But enough about me. Again, as I say, I'm going to repeat some of this, but please bear with me for those people who haven't been in the previous session. So again, in the Renesas ecosystem, there's lots of components to Synergy. There's obviously the device, and with the Synergy device, we're bringing through a lot of new technologies, and that's really fantastic. It's going to make a huge difference to the security of a lot of applications. We have the platforms, we have the SSP, delivering a lot of value in terms of software creation and how we get new products to market. And then there's the solution space. This is really important, and again, from earlier you'll have heard me say this. When we think about security, we have to understand the solution that we are going to generate. Security is not something that you can easily add on afterwards. You have to think about it holistically. You have to understand all of the stakeholders. You have to understand the attack surface that you're going to suffer. So where may attacks come from? Who's going to attack you? What is the value of the attack? What are their capabilities? So you have to think about all of this, and you have to understand what is the damage of an exploit. So there's a much bigger solutions-orientated part around security than we would traditionally see around other technologies. So this is not something you can just graft on afterwards. You have to think about the use cases, the value of what you're trying to build, and then figure out how you want to build it. And again, with Synergy, we have a bunch of great technologies which we'll go into for enabling this next generation of solution. So again, some of this framework is going to be similar to what some other people saw before. Again, relentless attacks on the Internet of Things. We'll have a look again at some of the requirements quickly. We'll go down into a quick review of the IoT security with Synergy, how we enable confidentiality, how we ensure integrity, and how we safeguard systems. And we'll cover that in the session, and then we'll have some Q&A, hopefully, at the end. Now, got a lovely picture here. This is one I found on the web of a lovely path. And I think that this is a very good analogy of security for a number of reasons. First of all, there is a path through here. We can see where we're going. People have been down here before. But it's a very narrow path. People haven't been off that very far. It's kind of rutted. Some people have got dirty. Some people have probably suffered going down this path. And probably just around this corner or hidden in the trees is an attacker ready to mug us if we go wrong. So it's a very good analogy to security. So we can think about this as, hey, this is fantastic. We know what we're going to do, but there are hidden dangers, there are hidden issues all the way along the road. And in this case, security is a science. Again, I mentioned this earlier. People live their whole lives doing security. I work very closely with some guys at the Royal Holloway University in London. And this is a specialist university for information security. And there are people there, who have been doing security for 30 years, 40 years. And they don't know it all. So there isn't an expectation that all of a sudden all of us will be experts. It is a pathway, it is a journey. And today, again, we're just going to scratch the surface of that. So a review of the advanced capabilities. We recommend, over and above this, go and learn more, go and educate yourself further on security. Hopefully we'll give you a good start on this. And of course, there's lots of material out there. I was asked a number of times just over lunch, can I recommend a good book? What should I go and read first? And my answer to that is the Embedded System Security book by David Kleidemacher. If anybody knows David, or you don't know David, he was CTO at Green Hills for a number of years. So it's a very good book. It's kind of written independently of Green Hills, so it's just a good overview of a lot of the security context. So what's your strategy for IoT security? And in too many cases, it's exactly this. Yeah, we kind of cross our fingers and hope that we've done enough. And that's rarely the case. So, you know, we've got to try and think through, again, how we're going to protect systems. What is the attack surface? What are the attackers going to do to try and break us down? Again, you've seen a lot of this, some of you before. Cyber warfare is pervasive. This is how bad it can become. So, again, the cost of a smart grid attack on the US is estimated at $1 trillion. And unfortunately, you know, this is a realistic prospect. Again, some of you will know the NSA did an audit of the US grid system, and they found it to be completely full of rats and other malware, so remote access Trojans. So the reality is the systems that we have built already are significantly flawed. We also know that we need to do security across the entire system, because attackers will focus on the weakest link in the system. So in this case, perhaps a connected light bulb. So this is a real attack where attackers had broken a connected light bulb, which was inside the trusted domain, the homeowner's trusted network, and we're using that to attack the PC to exfiltrate bank details. So, you know, from a personal perspective, I always believe that there is always some level of security required in every system. There's obviously going to be a huge array from the light bulb example to automotive, to defense, and aerospace. But we have to think when we're building IoT systems especially, how are we going to have multiple vendor systems sitting together? Who do I trust? How do I trust? How do I manage those systems? Now, big data requires security as well, and this is a great use case for the IoT. So, you know, big data and the analytics behind that are fundamental for the IoT. It's the fundamental value in many ways. We can connect more things and we can make more decisions faster. We can be more efficient. But if we're going to operate on big data, if we're going to trust the analytics, we have to trust the data coming into our system, whether it's locally or whether it's remotely throughout the globe. And trust can only be achieved through the secure device framework. We have to deliver that. So, and in our case, from Synergy, we can develop secure devices, so applications, IoT widgets. Then we can evolve that into trusted data. Only if we have the trusted data can we really deliver the innovative services which are going to push the IoT. Why is this important? Well, as of last year, and this was by General Electric, only 14% of factories were connected to the enterprise and connected to the internet, which, you know, given the issues that we have around efficiency, is a remarkably small number. So why is that? Well, it's because there's over 250 million attacks in 1 year on those factories. And as I said earlier, you know, as device manufacturers, we have to be right 100% of the time. The attackers only have to be right a fraction of 1%. So it's a lot harder for us to get it right than it is for them to get it right.
250 million, is that same sources or various sources?
That's again from GE. So the source of the attack. Oh, the source of the attack, sorry. So the question was, what is the source of those attacks? And that's generically all the different sorts of attacks. So from cyber criminals, cyber warfare, well, all of those above. The other interesting thing, in this session I really want to point on to this one, a lot of people view security as a cost. Yeah? They go, well, I've got to invest a lot more engineering. I've got to pay a bit more for my silicon. I've got to pay more for my software. I've got to do penetration testing. I've got to figure it all out. And it is a cost, but only if you don't view it holistically. If you can then develop new services because you can trust the data, there is a huge amount more value that can be generated from your product. A connected product which is leaking data should be worthless. A connected data which enables a new generation of services has intrinsically a lot more value in it. And just to put some numbers on this, this again from General Electric, this is all about the 1%. So what does a 1% improvement mean in each of these different markets? So a 1% fuel saving in commercial aviation would save $30 billion over 15 years. A 1% efficiency gain in healthcare, $63 billion. 1% capex reduction in oil and gas exploration, $90 billion. So we're not moving the dial very far to recover a lot of that investment. So by connecting these devices securely, by enabling new services, we're enabling a rapid saving in costs for a whole set of different markets. And so, I'm very much of the opinion that yes, security can sometimes be challenging. Yes, sometimes security can be difficult. But the output, if we can enable new services, is a massive change in efficiency for the entire industry. So while there may be an upfront cost, there is an awful lot more value in doing security right. So what are the major threats that we see? We can pull out some of those in marketing messages, but actually going back to this one, I think is the foundation. So a number of organizations kind of run a list of what are the critical attack vectors and things that should be improved. OWASP do one for top 10 for IoT. I actually prefer to go back to the Council for Cybersecurity. So the Council for Cybersecurity is a global NGO, non-governmental organization, focused on bringing through best practice in information security, InfoSec. The board of the council includes the ex-head of the NSA, the ex-head of the Secret Intelligence Service in the UK, ex-head of Symantec, and a whole bunch of other industry luminaries. It's run by the SANS Institute. And if we just look through here, there is these slightly darker ones. There's a whole set of things which can be applied directly to the Internet of Things. So an inventory of authorized and unauthorized devices, what does that mean? It means that we have to authorize our devices. We have to understand what is being attached. We have to understand when it's being attached. We have inventory of authorized and unauthorized software. What's running on our device? When was it created? When was it updated? How is it being managed? Who has access to it? It's not particularly rocket science in terms of the threats, but we don't see it applied so much to the IoT. Secure configuration of hardware and software. It's pretty brain dead. Of course it has to be secure. But what does that mean? Well, first off, it means switch off your debug. And in too many cases, products are still shipped with debug on. Okay, there are cases where we need to do that for RMAing and other things like that, but there's a problem here. And the number of devices with ports left open, and shipping, with the back door not just unlocked, but left open, it's incredible. We need to understand vulnerabilities. We need to be the first people to attack our own devices. Because there's a lot of attackers out there. They will come, they will try and attack your devices. So you need to be aware of what your vulnerabilities are before they are, so that you can roadmap them into your systems. We have to have defenses against malware, application software security, secure configuration for network devices. Controlled access is a very interesting one. With the IoT, it's not enough to just authenticate the device. Because you're going to have multiple users, you have to also authorize who is using and interfacing to that device. So we have to create some more complex solutions for how we manage our systems, how we imagine they're going to be built. So you have to have a view to how you expect these things to be interoperated, and you have to look at the security holistically. There are then some more advanced ones. You know, does your company have security skills in there? Who's in charge of security in your organization? Have you done penetration testing? An interesting one is incident response. I was in charge of this at ARM as we got more and more into security. You know, if there was a problem found in the architecture or microarchitecture or implementation of a device, what happened? In the same way as you know, you have a big problem with automotive, you have to have a recall. You do have to think about these things in advance. This is a bit high level. So let's come back down and focus on the challenges for IoT. Again, some of this I presented earlier. So 5 key security challenges. First of all, protecting intellectual property from theft. We had the demonstration on the Expo Hall the last couple of days showing how we can protect IP using the Synergy devices and using a secure kernel, secure boot mechanism, which allowed us to constrain intellectual property. We have to protect data in flight and at rest. We have to create robust foundations, the root of trust, identity, authentication, and authorization. We have to look at how we separate critical functions, and we have to manage the device over its life cycle. Many people saw that earlier. It's worth repeating all of these things because these are the fundamental things. No matter how you tackle them, no matter how you deal with them, these are still the 5 key use cases that you have to think about in your design. Again, underpinning those 5 are the core technological requirements of confidentiality. So using cryptography to limit access to information. Integrity, ensuring the platform is trustworthy. Something which is measurable, something which you can guarantee and you can stand behind. And then availability, so guaranteeing reliable performance in all conditions, including under attack. So let's try and link that back to Synergy itself. I think we've done enough of the high-level stuff. As I said earlier, I believe very strongly that security is a requirement across the Internet of Things. From the cheapest connected light bulb, connected widget, a door monitor on a connected alarm system, all the way up to the highest grade device, automotive, military, or whatever. Perhaps the first unique thing and the greatest thing about Synergy, from my perspective, is that we have applied security from top to bottom. And of course, there's some right sizing in there. So we see at the high end with the Series 7, we have all of the capabilities. But even here, on the Series 1, the Series 3, we have symmetric cryptography accelerators. We have the true random number generator. We have the limited JTAG access. And we have the unique identifiers. And over time, other ones of, you know, these boxes will, of course, be filled in as the platform evolves. So in here, we can see we've got our core functions. We have the symmetric crypto accelerators. So this is our AES, triple DARES, RC4, other accelerators in here. We have our asymmetric crypto accelerator, and this is acceleration engines for RSA and also for ECC. We have our hash accelerator, which allows us to ensure that the application and data is correct. We have our true random number generator, our asymmetric key generator accelerator as well, and also key secure storage. So we have a whole set of capabilities in here. So as I say, the first thing I really like is the fact that it covers from top to bottom. The second thing I really like is the focus on these asymmetric accelerators. I think that this is a highly differentiated capability in the microcontroller domain. And as we go to systems where we have to authenticate more often, we have to authorize more often, these things become more and more valuable, because otherwise the amount of computational time and power, performance taken, it really becomes a struggle for us. So these are the crypto functions. And then in terms of the integrity functions, we have three here. We have the limited JTAG access, we'll talk about in a second. We have the secure memory protection unit, we'll talk about the MPUs in a bit more detail in a second, and we have the unique ID. In terms of software, there's also a set of software components coming through. We have the crypto library, of course, so the APIs, we'll have a look at some of those as we go through. We have the secure boot framework. Again, this was what we were showing on the show floor the last couple of days. And then we have VSA components and QSA components coming through as well. So what I want to do is break down into the next level of information. First of all, in terms of confidentiality, obfuscation is not a solution. A lot of people have asked me in the past, how do I hide the keys? How do I hide information? And the answer is you shouldn't. In fact, it's exactly the wrong thing to do, because if you believe by hiding things, you're making them secure, you're deluding yourself, and you're making a very dangerous product. The reality is you should always assume the attacker has all of the documentation. You should always assume they have all of your code base. So they've bought a device, they've fibbed it, they've extracted all of the code base. And you should assume they have infinite time, because there's a lot of them out there. If you can make it, somebody can break it, and that's the reality. So instead, what we have to do is develop architectures and implementation where the only thing that we have to keep hold of is the keys. So that if a device is broken, okay, they've got one set of keys, but that is unique for that device. If they want to break another device, they have to break it all the way down. They have to fib it again to get the keys out. And of course, that's financially not viable for the attacker. It's hard for the attacker, and hopefully they'll find another target. So how do we do this? Well, we need to have a broad understanding of concepts and limitations of the technology, how we develop cryptography, understanding how ciphers and standard solutions like AES work is great, symmetric versus asymmetric, signatures and certificates, authentication, fingerprinting. If you can understand all of that, then you're in a great place. Alternatively, you can leverage the APIs which are available with Synergy, and it will get you through the problem an awful lot faster. So if we look at enabling confidentiality, true confidentiality can only be mathematically provable, in that we can use cryptography to mathematically prove that a system cannot be broken. Synergy is bringing this premier cryptography to the MCU domain. It accelerates performance, reduces our power, and it gives us a lot more simple API. What we've got up here is obviously all of the different engines inside the Synergy security engine. We've got our true random number generator, we'll talk about that in a second, AES, DES and symmetric, asymmetric, some other symmetric components here, SHA-1, SHA-256, MD5, GHash, and RC4 stream cipher. And then we have our secure key storage over here as well. Benefits of this: gives you a minimal attack surface. Because the CPU is not operating directly on the data, you can reduce the amount of information leakage in the system quite substantially. It's got some integrated alarms. So in effect, it's got a state machine in there. If you try and attack it and force it to start leaking information, you'll actually trigger a bunch of alarms. And that can then be used to either brick the device or throw it into an exception handler and prepare a response to that, which, as I say, may be to brick it, it may be to reset the device to thwart the attacker that way. And of course, it's got this very simple API. First of these blocks at the next level of information. So Entropy is very critical to secure systems. Cryptography relies very heavily on complex and variable keys. In the secure boot process, which we have developed in concert with Renesas, we develop a very highly random 512-bit seed. And that 512-bit seed then goes through a set of key derivation functions to produce the key. If your true random number generator is not high entropy, those keys themselves will start to leak information very, very quickly. In terms of this block, it's NIST SP890 compliant. This is the latest specification for Entropy. It really is the best in class. And again, you know, it's worthwhile really focusing on, because this is a true differentiator for Synergy, and it's a true differentiator for platforms leveraging Synergy. If you're not using a true random number generator, you're using a pseudo random number generator, the likelihood is somebody will break you relatively quickly and relatively easily. So, you know, I can't stress enough how important this block being right is. It's managed within the Synergy security engine. A software attacker can't easily force it or manipulate it. This is a standard attack on devices. If you can get in and you can force the random number generator, either through heating the device, cooling the device, changing voltages, then you can start to break down the devices. You reduce the entropy and you reduce the amount of attacks that you need to figure out to make it work. So the fact that we guard against all of those makes the true random number generator a really key part of this. And it's very, very easy to use. So the nice thing as a Synergy user is, you know, it's there, you know it's there, but you don't have to really understand the technology which is making it work. You can if you want to, but all we have to do to read it is a very simple function call. So, as I say, we support in Synergy all of the major symmetric crypto blocks. From a IoT perspective, again, really AES 128 should be your absolute baseline. While it's great to have things like triple DES included in Synergy from a legacy perspective, it's not where you should start any system design today. Of course, symmetric cryptography uses identical keys for encryption and decryption, so the stakeholders must implicitly trust each other. And keys have to be shared in advance to avoid attacker access. So we have some powerful cipher support here. AES should be good for industrial applications for 20 years. Low power, simple application. In terms of AES, again, some really nice, simple function calls here. So in terms of setting the key, we just literally need to bring it in. We've got the key itself, key length, key schedule, and that allows us to define which of the key lengths we're going to use here. And then in terms of the actual encryption, again, very simple function call. What's its length? What's the plain text in? And what's the cipher text out? So we don't need to know a lot about what's going on inside there to actually start using cryptography. This table is incredibly important. Cipher agility is going to be one of the big challenges of the next 20 years. The nature of ciphers is they run out of time. We have people attacking them, whether it's quantum attacks or whether it's just brute force attacks. Eventually, AES 128 will not be sufficient. So what do? Well, you can either go and buy a new chip. That's okay, I guess, and it's a good business model to sell new stuff. But if something is deeply embedded, then we need to be able to move it forward. And in this case, with the Synergy devices on the 7 and 5, we support 192-bit, which you may want to go to because it's obviously a slightly lower performance hit, or alternatively the 256-bit. So we have crypto agility in there. We also have a bunch of chaining modes. These are really, really important. The basic ones are CBC and EBC, electronic code book, and the cipher block chaining, which allow us to add lots of different encryption packages together. We also have the CTR and the other ones. And again, all of these main chaining modes are included. If you look at competitive solutions, they will normally have one of these. You won't have enough capability in there to deter attackers over the long term. You may also, if you think that you're being attacked, you may want to change the chaining mode at some point as well. So these are additional protections in the framework of how we think about security. In terms of the asymmetric ones, of course, the whole nature of asymmetric is that the public and private key are different. They're generated through a trapdoor equation, which is very easy to do in one direction, but very difficult to do in the other direction. So in the case of RSA, you can generate two primes, you can multiply those together in a modulus way, and you can come up with an answer. But taking that answer and trying to regenerate the primes is incredibly difficult. Now, you then generate, obviously, the public key and the private key. Doing it this way doesn't necessarily mean that the message came from a trusted source. It just means that somebody's got your public key. So you do have to be careful, of course, that just having the cryptography on its own doesn't prove that the message is correct or it came from the right place. It just means that somebody has the key. Again, lots of advantages with having it in the secure engine. But fundamentally, again, as probably many of you know, it's an and between asymmetric and symmetric encryption. Asymmetric is very challenging, it's very computationally expensive, even with an engine. So this has to be focused on authentication of devices, onboarding, creating secure channels, whereas symmetric encryption is ideal for very fast, low-power encryption. But once you've got the key, you've got access to everything. So really, from a security perspective, it's an and. Again, I'll refer back to hopefully what some of you saw on the show floor yesterday, where we had the secure boot mechanism for uploading new firmware into a device. The way in which we did that is that we took the binary for our code and we encrypted it with a 128-bit key, which was really, in effect, just a high-entropy random number. It just been generated on the PC. That key in and of itself, is temporary. Doesn't exist for long. What we have to do, though, is we can take the encrypted blob, we can fire that across the internet, it's encrypted, so it's fine. But then what we have to do is we have to take that symmetric key, and somehow we have to get it to our manufacturing line and onto the device. And we use the asymmetric component to create a very strong tunnel between the device which is delivering the keys and the inside of the chip to create that secure, robust tunnel which we can then inject the symmetric key through. So on there, we also have the hash block. We use hashes for creating unique fingerprints. And really, it helps us prevent modification of data. So this can be things like a man-in-the-middle attack or a replay attack where there's timing modification. So very simple example of this. Again, if you guys know all about hashing, I apologize, but for the people who don't, here we can see two sentences which are the same apart from one letter has been slightly changed. The nature of a hash means that the output when we do the hash is radically different. And in most cases, there is sufficient differentiator there. If we use SHA-1, it is theoretically possible today to create identical hashes. If we use SHA-256, which again is part of the NSA Suite B capability, then these hashes are sufficiently different and sufficiently robust that we should be able to protect against man-in-the-middle attacks, injection attacks, and others for the next 20 years or so. So there's a very good block there in terms of the SHA, the G-hash, and others, again, which allow fast operation and relatively low power operation. So let's look at how we would start to set up a system. And confidentiality is critical here. So we may have a gym, we may have a running machine. We've got various different stakeholders in here, the actual athlete himself, people who have some responsibility from the machine, predictive maintenance, equipment leasing, gym ownership. Because of asymmetric encryption, we can share data with each of these independently without giving away the private information of the runner here. At the same time, we could use an envoying technique, perhaps with some personal keys inside the next generation smartphone here, to deliver those keys onto the running machine and tunneling through the cloud. That means that we could take this person's information and send it to his physician or his surgeon or others. And from my personal perspective, this is important. My father-in-law had a heart valve replaced, and he then had to go to some specialist gym sessions where there was a nurse in case, you know, he collapsed. Whereas if you could apply your personality to the machine in a secure way, you can share information a lot more broadly without surrendering any privacy. It's all about keys, and it's all about key exchange and key management. So here's this example, and here's how we would use Synergy for this. So we may need to do some pre-provisioning. So we perhaps have our watch here. So we're passing over a public key for our watch into our user cloud. We are taking a key from the medical guy and putting it into our personal cloud as well. We are going to pass over a key from our application and our medical back over to our watch. So in effect, we are saying this watch now contains all of the keys for our doctor, our surgeon, or whomever. So we have a secure mechanism for exchanging keys in advance. If we go to the gym, we would generate an on-the-fly public-private key pair. Why on the fly? Well, because for each user, for each session, we want this to be unique so that it can't be traced back to us. We would then do some NFC pairing, perhaps between our watch and our running machine. We'll pass over the public key for the watch, and we'll pass back the treadmill public key as well. We can then use the envoy to set up a symmetric session between the watch and the running machine. We can pass those back. We can create then an additional tunnel via our watch back to the medical professional. We now have a secure tunnel from this machine, which is in a random gym somewhere in the world, to our own private doctor. once we have that tunnel, and only when we have that tunnel, can we actually create a symmetric key which we will use to pass the data. So it is all about the keys. It's all about how we set up these private tunnels and how we pass information. Now, of course, we then bring that back to Synergy itself. So we're using asymmetric key generation up here, the true random number generator, some secure storage, and the unique identifier to create this session. At this point, we're going to use some asymmetric acceleration to pass these across, some secure storage, unique ID, transport layer security, and the crypto lib to pass information through the tunnel. And in this last part, we're going to use everything apart from the key generation to accelerate our application. The interesting thing is we have created an incredibly high value differentiated application out of the same piece of silicon. Never before have we been able to identify a person on a random piece of gym equipment in a random gym and pass that back to our doctors without having to share that same information with the stakeholders in the gym manager, the person who perhaps owns the machine, the person who does the predictive maintenance. I don't want my personal information going to everybody. I only want my personal information going to my doctor. So we're developing the capability for a brand new set of applications, but it is of this level that you have to think about how the keys are going to be passed and how we're going to manipulate these things.
Does the session have a length of time? Or?
The question was, does the session have a length of time? And you should rotate keys relatively well, but no, there's no real absolute number on that. So integrity is critical as well in here. Traditional embedded systems were not connected. So Synergy has been enabled to develop this root of trust, device personalization, protected memory, management of certificates, and secure boot. We also have the JTAG key in here. This is a 128-bit debug access key. Roughly, it'd take a billion years to crack that, social engineering notwithstanding. If you set it all to ones or you set it all to zeros, it takes less time. You'd be surprised. So that's fine. In terms of securing memory, the memory protection units are really, really important. Memory protection units are a key differentiator in the Synergy devices. So we have here the existing Cortex-M1, we have the bus master and bus slave, and then we have the secure memory protection unit as well. This allows us to isolate different components away from each other. So again, if we look at secure manufacturing, the application that we showed on the expo floor here, we can personalize keys and send them through a secure mechanism to the manufacturing. We can encrypt the application. We can send those keys through. We can validate, and then we can program that. Again, in this sort of session, we need to limit the debug. We need memory protection. We need asymmetric keys. And lots of the other functions create this type of application. Safeguarding availability is also really, really critical. Here's an example I like, again from personal experience. And forgive me if you've heard this one before. So my eldest child was born prematurely. 7 weeks. He was very, very small. So we had to have him connected to a monitor for about the first 12 weeks of his life. And that was great, apart from we never got any sleep because the monitor kept going off. Today, thankfully, we're seeing more and more devices. But what would be great is if we could connect that type of device to other systems in our smart home. So connect it with the lights and with the alarm clock so that we wake up. If the baby stops breathing and the lighting between our room, and the baby's room all come on automatically. The interesting thing here is we've taken three very disparate, semi-useful types of devices, and we've created potentially the most critical alarm system you will ever own as a parent. So we can start developing new novel applications. Now we can also send data out and to the Bluetooth. If we can get security right, we can then also start adding value. We can send the data out, perhaps to the physician again, or to the doctor. We can bring in context, such as the weather report. The challenge that we have is as we build more and more devices, how do we manage those? So again, application support from the OEM and home monitoring. So we are building, again, lots of devices in the IoT which need to connect, and they need to have security between them. They need to be trustworthy information sharing. And again, we go back to the key exchange mechanisms that we were talking about earlier. Availability is really important. If we look down at the baby monitor, for example, there's a set of things that may become infected. IoT system behavior and communications can become affected. Whereas the sensor, configuration, and alarm, we want these to become completely inviolate. We don't want those to be harmed in any way. So again, with Synergy, we can separate and we can isolate these different components from each other. And we can do this using the memory protection units to create a robust secure boot underneath these ones. We can contain these inside the supervisor mode and these ones inside the user mode. So we have a layer of separation. I think I've run over time, so apologies for that. Synergy, very extensive, very easy to use, very powerful, and ultimately very, very secure. So security is not an afterthought. Cryptography is not sufficient on its own. We have to think about this in a wider context. And we need to leverage the right tools and industry best practice to achieve this. Okay, apologies, I ran a little bit over there.
I think you have an hour, right?
But do I have an hour? Yeah, you could for another 5 minutes. Okay, wow, okay, we've got plenty of time for questions. There we go. I knew I was bang on time. So, fabulous. Okay, so thank you very much for that. Hopefully it was useful. Are there any questions?
So you talked about using a hash to verify integrity, and my understanding is you really want that to be a massive key, like an authentication code, which requires
You can.
key. Should that key be separate than the key that's used for the encryption?
Yes. So the question is, when you're doing the Mac, or you're looking at the integrity of the code, should that be a separate value? Yes, you do want to manage that, and you do want to manage the integrity over the longer term as well. Okay, sorry.
Just want to clarify. Earlier I asked about the 150 million attacks you mentioned.
Yes.
Out of how many sources? How many sources are generating? Do you have an estimate of?
It's a good question. So the question down the front here was, out of those 250 million attacks that we spoke about earlier, where are they coming from? It's difficult to put a number on. I haven't seen an exact breakdown. It depends very much on the types of industry that people in the more heavy industry, they tend to be nation-sponsored. We're seeing a small but growing number of cyber criminal type attacks, so ransomware and things along those lines. And then there's the occasional drive-by as well.
I see. So are we talking about like thousands of attackers generating this many million? Or?
So the question was, are we seeing thousands of attackers developing these attacks? I think it is a large number. I think obviously, again, it depends on the exact domain, but some attacks come from a very narrow set of attackers, nation states, but other ones are very broad. And there's a lot of people trying to break this, as we've seen with the automotive stuff. You know, there are universities, there are people who are doing it for financial gain. There are people just trying to do it to break things.
And one other quick question, the public key, you mentioned manufacturing.
Mm-hmm.
So if you have a certain product, let's say 100,000 product, like the same part number, all of them would have that?
Okay. So there's a question there about the keys. So if you're producing 100,000 devices, would they all have, in effect, the same key? And the answer is absolutely not. So there is a requirement for the keys to be unique to the device and to have a high entropy between those different devices. The next question is then, how do you get those keys on the device? And what Renesas is looking at the moment and moving towards is injecting unique keys at birth as part of the manufacturing process. And there's a couple of ways you can do that. You can use the TSIP itself to generate a private public key. The nice thing about that is the private key then never leaves the crypto engine. The other way is to use what's called a hardware security module, HSM. These are very, very expensive custom security boxes by people like Thales. And you can attach one very close to the device through the manufacturing process. But each of those devices will have a unique private public key pair.
Follow up to that question, would that mean that your firmware updates would have to be coordinated per device as well?
So the question there is, would updates need to be unique or recompiled for each device? The answer is no, they don't. So again, with what we showed on the demo, your software can be encrypted with a symmetric key. So you encrypt it once, and then you take it out. And what you're doing is, when you're talking to each device, what you're using is the public side of the key, the certificate, which is signed against the Renesas key, in this case, to prove that it is a right device, and then you can pull that out. You can either do that and say, okay, well, I'm going to apply that to all Renesas devices. That's fine, that's perfectly possible. Or you can say, okay, well, here's a range of identifiers which I will allow it to update to. So compile once, deploy many times, again, using the asymmetric key pair. What you do have to have is a secure tunnel to get that key manifest into the device so that you can then decrypt the application, the update on chip.
So in the example you used with the running machine, would each one of those devices in that chain have to have the same peripheral set? No, they wouldn't. So the question was, on the running machine example, would they all have to have the same peripherals? Absolutely not. I think, all that you would need is the ability to, in effect, inject your key information through, again, an encrypted link, and then that would allow that machine to communicate whatever data it had back to the medical professional. So that could be a different manufacturer, it could be a different way. Of course, the application side of it would need to mesh up, but the peripheral set wouldn't necessarily need to.
You talked about the need for high-quality entropy and key generation, and I'm wondering what are the other standard methods for measuring the quality of entropy, and kind of what are those? And I realize that may be a broad topic in and of itself.
Yeah.
And has the Synergy platform met some sort of standard for quality of entropy? Is there an agreed-upon standard for that?
Yeah. So the question there was the level of entropy. How do you measure it, and are there standards around that? There is the NIST standard, which I pointed to, so the 980 standard, and there is the A, B, and C. I think it is evolving on those. So with Synergy, we adhere to that, and we adhere to the leading edge of that specification. And that there are a bunch of papers. If you go to NIST,
you can read about yay much documentation on exactly what a true random number generator versus a pseudo random number generator must be, how it should be measured, and all of those different capabilities. It is a science again in its own right, entropy and how you develop that. Any others? Okay, also.
I noticed on one of your slides you had the API to generate a random number, and it was 32-bit, but you want to generate a 128-bit key, so you just call it 4 times in a row and get your 128, or is there a
so the 32-bit is a pointer to it, I believe. So,
okay.
so it remains 128. Okay, we're out of time. Thank you very much.